Hello, I am Ryan Campbell. Today we will discuss a new proof of three-colorability of Eulerian triangulations by Mu Soon Se and Douglas B. West. The basic idea behind the three-color problem is that we want to know which planar graphs are three-colorable. This brings us back to several definitions we have studied. Planar graphs have embeddings where edges do not cross one another. Three-colorable graphs can be separated into three independent sets of vertices. Each set is given a color, and since the vertices are from independent sets, no two adjacent vertices share a color. Included here is some research about three-colorability and why we actually only care about sufficient conditions. Stockmeyer proved that it is NP-complete to determine whether a planar graph is three-colorable. So mathematicians have instead spent their efforts finding sufficient conditions for three-colorability. By Groch's theorem, triangle-free planar graphs are three-colorable. But what about planar graphs with triangles? That is something we are going to focus on today. In the 19th century, there was the claim that triangulations are three-colorable if and only if every vertex has even degree. This was later proven. Recall that triangulations are plane graphs where every face is a triangle. Near-triangulations are plane multigraphs where all bounded faces are three cycles. The unbounded face does not have to be a three-cycle. It has also been proven that near-triangulations are three-colorable if and only if every vertex has even degree, similarly to regular triangulations. Eulerian graphs are going to be one of our main focuses in our proof, especially Eulerian triangulations. We have studied Eulerian graphs this semester. An Eulerian graph is a single circuit traversing all edges exactly once. A graph with all even vertex degrees is considered Eulerian. As we discussed on the previous slide, triangulations and near-triangulations are three-colorable if and only if every vertex has even degree. We can now rephrase that to be triangulations and near-triangulations are three-colorable if and only if the graph is Eulerian, because all graphs where all vertices have even degree are considered Eulerian. Although this has been proven, we will discuss a new method of proof using the fact that Eulerian plane graphs have non-crossing Eulerian circuits. We will cycle through our three colors to achieve our proper coloring. We will also use the idea that the number of edges is divisible by 3. We have 3 lemmas that are going to assist us in our proof. Lemma 3.1 says that every Eulerian plane graph has a non-crossing Eulerian circuit. And while I'm not going to prove that to you today, we are going to take a look at what that means as an example. So in this drawing we see an Eulerian graph, and we know that because every vertex has even degree. It is also a triangulation, a near triangulation. Every face that we see that is bounded is a triangle, but we can tell that the unbounded face has 6 edges, so the unbounded face is not a triangle. So it's a near triangulation Eulerian graph. So we want to show that this first graph is a crossing graph. Okay. If we begin at A and travel over both red edges to get to B and then D, when we loop back around to get from C to B to E, the blue edges cross through the red edges. Vertex B is kind of like a traffic intersection in this case. Okay. Below the diagram, I have listed the Eulerian circuit A, B, D, C, B, E, A that we just discussed. In the second drawing, though, we are going to have a non-crossing Eulerian circuit. And that circuit is going to be A, B, C, D, B, E, A. In this drawing, if we start at A and follow the blue path and then the red path, we have not traveled across a previous path. We have touched that previous path at B, but we have not crossed over it. In fact, if we slice horizontally through vertex B from the second drawing, we can separate the embedding into a simple closed curve. This closed curve has basically the same Eulerian circuit as our second drawing, which was a non-crossing Eulerian circuit, except since we have split up vertex B into B and B prime, the second time we reach B, we're actually reaching B prime. Lemma 3.1 allows us to repeat this process at every vertex with degree higher than 2. And of course, since these are Eulerian circuits, every vertex with degree higher than 2 has a degree of 4 or 6 or 8, some multiple of 2. The other two lemmas, lemma 3.2 and 3.3, are discussed on this slide, and I am going to go through the proof of lemma 3.2 here. Lemma 3.2 says that in every Eulerian near triangulation, the number of edges is divisible by 3, and we prove this using induction. And we induct on the number of bounded faces. So let's begin with a non-trivial Eulerian near triangulation, and let's call that graph G. F is a bounded face containing an external edge. So this would be one of those edges that is also on the unbounded face. We get our G prime graph from G by deleting the 3 edges of F. Okay. Then, since G prime is a disjoint union of smaller Eulerian near triangulations, the induction hypothesis implies that its number of edges is divisible by 3. And since that graph, G prime, its number of edges is divisible by 3, it is going to hold for G as well. Lemma 3.3 states that in a non-crossing Eulerian circuit of an Eulerian near triangulation, the length of every subcircuit is divisible by 3. So this calls in a new vocabulary word. We have a subcircuit of a circuit C, and that is a portion of C that is between 2 visits to a particular vertex. So if we go back to our drawings here from lemma 3.1, in that center drawing, we have the Eulerian circuit A, B, C, D, B, E, A, and a subcircuit of that would be B, C, D, B. So it's starting with B, ending with B. And now our feature presentation, the new proof that every Eulerian near triangulation is 3-colorable. Graph G is an Eulerian near triangulation. The numbered edges indicate a non-crossing Eulerian circuit of G. So if we start at C, we follow the arrow, which is really a non-directed graph. I'm just showing the arrows and the numbers on those edges so that this presentation will be easier to follow. Notice vertices D, F, and B. D, F, and B all have degree higher than 2. Okay? They both have an in degree of 2 and an out degree of 2 because we have 2 edges coming into each of those vertices and 2 edges coming out, which of course those have to be matching numbers. Okay. As we reach, let's talk about D. As we reach D from edge 1 and exit through edge 2, when we come back to it, we are entering through edge 4 and leaving through edge 5. Now, the way that we have this set up, it is a non-crossing diagram. If we had, however, gone from 1 to 4 and then 2 to 5 all through D, that would be a crossing diagram, and this proof would not be valid. So let's begin at a vertex, and let's pick C. We are going to assign C the color red. As we travel around the non-crossing Eulerian circuit, we assign each vertex a color, red, blue, green, red, blue, green, continued until we have reached our first vertex C again. So let's start with C. We have it red. Then the next color in the series is blue. So after we follow edge 1, D is blue. Following edge 2, E is green. And then since we've gone through our 3 colors already, back to the beginning of the pattern, F is going to be red. Now, edge 4 leads us back to D. But since from D to D again, this small sub-circuit from D to E to F back to D, that sub-circuit has length 3. We are back to the same color in the pattern. Okay, so D ends up taking up our blue spot. Okay, after D comes B, following edge 5. Green is next. Then follow edge 6 to F. Red is next. F is already colored red because, again, from the first time to the second time that we have reached F, we have gone through 3 edges, and 3 is divisible by 3, of course. Okay, next we follow 7 and go to A after red is blue, so A is blue. And then A to B. B is already green, and that's the next color in the series. And then back to C, which is red again. Or red still, rather. We have completed the Eulerian circuit and explicitly assigned distinct colors to each vertex. So we have shown that in this Eulerian Near-Triangulation, the number of it is a 3-colorable graph. What I find most interesting about this proof is that it is a fast algorithm to create a coloring. We can also picture the graph as we split the graph in lemma 3.1. So we could take vertex D up there at the top, and we could split that into D and D prime. Okay, so edges 1 and 2 would remain intact with D, and then edges 4 and 5 would instead meet up at D prime. Okay. If we did that at F and B as well, following this same circuit that we just discussed, we would end up with our simple closed curve. And the pattern would remain the same. So D and D prime would both be blue, B and B prime would both be green, F and F prime would both be red. So it's just kind of nice to think about this as that closed curve. Of course, each time we reach the vertex that has been split, we have traveled over a multiple of 3 edges. So by lemma 3.3, B is assigned the same color as B prime, and so on. Thank you for listening and watching my presentation. I hope you learned something about Eulerian near triangulations.